Hi, welcome back. And today we're going to talk about another theorem called the uniqueness of power series theorem. And so what this says is if we let two series be equal. So it says let this series, which is the series of c sub n times x minus a to the n. So this series is centered at a, this power series. And then we take another power series, d sub n, times x minus a to the nth power. And we let these two series be convergent. So we take these two convergent series such that they're equal to each other. Okay? Now, and they're equal to each other for all x in the open interval containing a. Then we say that c sub n equals d sub n for all n greater than or equal to 0. So in other words, the coefficients are going to be equal for all values of n greater than or equal to 0. Okay? And so what it is saying is that power series representations are unique. Okay? Okay, so what's the proof for this? Well, let's start by, again, going from the assumptions, and let's just take two of these series, and let's say that start with them being equal to each other, and also assume that they are convergent on for all x within the open interval of a. Okay. Okay, so the proof goes something like this. So let n equals 0 to infinity of c sub n, c sub n centered at a. Okay, so we're going to use these as power series representations. Excuse me. Oh, hold on. Oops. Let x equal c sub 0, plus c1 x a plus c2 x minus a squared plus okay, and it just keeps going like that. And let's say that this is also equal to d sub 0 plus d1 x minus a okay. So now, if this is true, so we let this be true, right? So if we can represent f of x equal to this and f of x equal to this, so these two are equal, then what happens? Well, if I take f of a what happens? Well, f of a equals c sub o, which equals d sub o. Why? Because at x equals a, all of these terms that involve x go to 0. And all we're left is with the first two constant terms. Okay, so there's 1. Now, if I take f prime of x, well, f prime of x, so I'm going to take the first derivative. So since these are convergent power series on this interval centered at a, then I can take the derivative term by term for both of these. And so I get f prime of x equals c1 plus 2 c2 x1 minus a plus 3 c3 x minus a squared, and so on. And then that also equals d sub 1 plus 2 d sub 2 x minus a plus 3 d sub 3 times x minus a squared, and so on. Now what I get is f prime of a, right? So f prime of a is going to equal c1, which equals d sub 1. For the same reason, right? So all these terms that have x minus a in them go to 0 at x equals a. And if I take the second derivative, let me do this. So if I take the second derivative, let's go back up to here, start up here. If I take the second derivative of the function, again term by term, now these will go to 0, and then this, I get 2 c2 plus 3 times 2 times x minus a, right? Which is also equal to 2 d sub 2 plus 3 times 2 x minus a, and that continues on. And similarly, f double prime of a is equal to 2 c2 which equals 2 d2, which then leads us to c2 is equal to d2. Now, more generally, okay, so if I keep going, this is going to continue. So, more generally, f to the nth power, the nth prime, so the nth derivative of the function is going to end up let's see here. No, actually, let me do this. So what we're going to end up getting is, more generally, it's going to be the nth power value at a is going to give us n factorial of c sub n is equal to n factorial d sub n, which then leads to c sub n is equal to d sub n for all n greater than or equal to 0. And that's the proof. Have a great day.